My talk will be about Gorenstein finite-dimensional local algebras. Unfortunately, I will speak English, blame Panania. Yes. So, some of us in recent years was interested in local algebras, and Gorenstein local algebra, it's an interesting subclass of local algebras. And the goal of my talk is just to give a different characterization of Gorenstein local algebras. So let us consider a vector space. And we know that there is a dual vector space. And we know if we consider some linear map between vector spaces, then there is a dual map in other direction between dual vector spaces. And these correspondence behave well, so if we consider some exact sequence of vector spaces, then we can consider dual sequence. And if this sequence is exact, then this sequence is also exact. And moreover, if when V is finite dimensional, then, as we know, the dual to dual is isomorphic to V. And it helps us when we study linear algebra. It's very useful. But situation for commutative rings is bad. So if we consider some commutative ring, and we consider some finitely generated model, then we can try to define dual model. I will note by uncheck. So just as homomorphism from R, from M to R as M models. And these correspondence behave badly. So for example, if we consider just Z2 as Z model, Z model is the same as just an abelian group, so Z2 is Z model. And if we consider a dual Z model, there is no non-trivial homomorphism from Z2 to Z, so at the end it's just 0. So exact sequence will not go to exact sequences, and we don't have anything like this. So, but in my talk, we will not discuss general commutative rings. We will discuss commutative algebras. So, the base field K will be algebraically closed, not necessarily characteristic 0. So, A is a commutative associative algebra with unit dimension of A over K is finite, and A is local. So there is a unique maximal ideal which I denote by M. And I will recall some basic facts about finite-dimensional local algebras. So, first of all, we can consider the quotient A by M. So, as we know, it's a field. And since our algebra with unit, the field K is naturally embedded in this field, but K is algebraically closed, and this is a finite extension of K, yes, because A is finite dimensional, so it will be just a finite extension of K. So we have that it's just a K. And
but if K is not algebraically closed,
yes, it is not closed. So, and it implies that A is a direct sum of vector spaces, one generated by the unit, and the other one is just an approximative. And if we consider a chain of ideals, we have M squared, etc. So I recall that there is a Nakayama lemma. Which says that if we have a finitely generated model such that m equals to m, then m is 0. It's true for any local ring. And so if at some point we have mk equals to mk plus 1, which is m by mk. So we obtain that mk is actually 0 by the Nakayama system. So the exclusions are strict until we get 0. In particular, all elements inside M are nilpotent. So, and we can consider just dual vector space. So, for any finitely generated model, we can consider just dual vector space. And actually, it's an A model. So if we choose some linear function, then we can act by an element of A on this linear function. It's just in the following way. The function A lambda on an element M is equal to lambda AM. And it's not difficult to check that it's a well-defined structure of a model on this thing. It's called...
when we act by groups, we should put inverse, because otherwise this is not an action.
Yes.
And what about this situation?
We have a commutative ring, so everything is fine. So it's a model. And it's called Matlis dual model. Matrix duality is a more general concept in commutative algebra, but in this particular case, it looks like just.
The lucky guy Malkis put his name on such an obvious concept.
So, since it's just a finite-dimensional vector space, yes, any finitely generated A model is just a finite-dimensional vector space, this functor will be exact. So we have is exact. So exact sequences will go to exact sequences, and it's duality. So 10 equals to of course, not always m equals to dm. Let's consider a simple example.
This is saying some statement that this is an exact function.
Well, it follows because M is finite-dimensional vector space, and we know what we apply duality.
It has nothing to do with more. This is a question of finite dimension.
Yes. So consider an algebra A, k of x, y, modular x squared, x, y, y squared. So it's a three-dimensional local algebra. The elements 1, x, and y form a basis. Maximal ideal is generated by x and y. And we can consider an element A and in this basis, this element x on A by the following matrix. And if we consider dual space,
so on the diagonal we have C0, C0, C2.
C0, C2. In dual basis, we obtain a transpose matrix. So, and if we choose some element, so let denote by E1, E2, E3 is a dual basis to 1, x, and y. So if we take an element B, then if B2 or B3 is not equal to 0, yes, let's calculate annihilator of B. So the set of elements which annihilate B. So if B2 or B3 not equal to 0, then C0 is 0. And we also have some linear equation on this elements C1, C1 and C2. So annihilator will be one-dimensional. And for E1, annihilator is two-dimensional. And if we consider all annihilators on this model, then X and Y have two-dimensional annihilators. Yes, because MX trivial on X and Y. So here we have only one dimensional line without zero, which contains element with two-dimensional annihilator. But here we have two nonlinear, linearly independent vectors with two-dimensional annihilator. So as a models, A is not isomorphic to E of A. And this model is called canonical. We will denote it by omega A. It's E of A. Canonical model. And the first definition of Gorenstein algebras is the following. A is Gorenstein if and only if A is isomorphic to its canonical model, omega A. So we saw an example of not Gorenstein algebra. Now let's give another definitions for any M model, model M. We can consider the circle of M. It contains such elements which are annihilated by maximal ideal. It is a submodel in M. And theorem that the following conditions are equivalent. First, A is isomorphic to omega A, canonical model. Second, omega A is one generated as an A model.
What does this mean?
It's an A model, so there is an element such that it's inside this model, such that omega A is A for some lambda. Third, that the dimension of circle is 1, and fourth, there is a linear function such that the kernel of this linear function intersects trivially with circle.
What is the source of your talk? Do you produce this by yourself? Or
No, mostly of that is taken from Eisenbach book, the last chapter about Gorenstein algebras, and but some things are from some other sources from internet. For now, mostly of this is from Eisenberg.
But Eisenberg doesn't consider finite-dimensional algebras.
No, it's at the beginning of chapter about Gorenstein algebras. He talks about zero-dimensional local algebra, but zero-dimensional means group dimension. So finite-dimensional is a particular case of.
So this theorem gives us 4 good definitions of Gorenstein algebras.
Yes, it's 4 definitions of Gorenstein algebras. Yes, let's note one property of so-called before we prove. So if we have some ideal then it intersects with so-called non-trivial. Well, it again follows from Nakayama lemmas because we have the following sequence. I is contained in mi, m square I, etc. And by Nakayama lemma, we will finish on 0. But this means that this ideal is contained in I, but it also is contained in the circle. Because when we multiply by any element of M, then we obtain 0. So let's prove this theorem. The equivalence of third and fourth point are trivial. Well, if circle is one-dimensional, then we can consider some linear function which doesn't contain that circle, and vice versa. From 1 to 2 is trivial, because if A is isomorphic to omega A, but A is always one generated. Yes, A is generated by yes. So from 1 to 2 is also trivial. Let's go from 2 to 3. So we have some linear function which generates our canonical model. And suppose that the dimension of circle is at least 2. Then there is an element inside intersection of circle and the kernel of this linear function. There is a non-zero element which inside intersection of kernel and but any linear function has the following form. And if we apply it to B, then it's lambda AB. So if we take A is A0 plus A1, where A0 is a constant and A1 from maximal ideal. Then since B inside circle, a1b will be 0, so it's just lambda a0b, but a0 is just a constant, so it's a 0. So we obtain that any linear function is equal to 0 on A, but it's not true. Yes, we can find that any function which is not equal to 0 on A. And if you want to go from 3 to 1, so again, let's go from 4 to 1. We have such function, and we can just construct an isomorphism. We can consider a map from A to omega A, which sends an element A to A lambda, where lambda is this function. And of course, it is a homomorphism of A models. And it's enough to check injectivity, because it's finite-dimensional vector spaces of the same dimension. So let's check injectivity. So if A lambda is equal to 0, then A lambda on B equals to 0 for all B. But by the definition of action of A on linear functions, we obtain that lambda AB equals to 0. So lambda is equal to 0 on ideal generated by A. But this ideal intersects with circle, as we mentioned. Any ideal intersects with circle. So, but lambda is non-zero on all non-zero elements of circle. So we obtain a contradiction. So it's not A0. So we proved this theorem, and there is another characterization of Gorenstein algebras, but this characterization actually trivially follows from this theorem. There is a notion of Frobenius algebra. I don't know much about Frobenius algebra, but still. So let B be finite-dimensional universal associative algebra. Then we say that B is Frobenius.
Not necessarily condition.
Not necessarily condition. B Frobenius. If there is non-degenerate bilinear form, sigma such that the following condition holds. So the simple example of Frobenius algebra is the algebra of matrix. Here we can consider a trace of product. And also, it's not difficult to check that if G is finite group, then the group algebra of KMG is also continuous.
But this is just not degenerate by linear, not necessarily symmetric or anti-symmetric.
Yes, yes. So if we have a Frobenius algebra, actually it's equivalent. We have a linear function such that the kernel of this linear function contains no non-zero left ideals. So how we can construct this function? If we have this form sigma, then we can construct lambda as lambda on p equals to sigma 1b. Yes, and if kernel contains some left ideal, then well, it contains then principal left ideal. But it equals to sigma bb, but our form is non-generic, so this cannot be identically equal to 0. And in other direction, if we have a linear function lambda, then we can construct this form just by lambda of AB. Well, it's not difficult to check that it will be not degenerate, and it's always this condition holds. So, local Gorenstein algebras are exactly commutative local Frobenius algebras. Because we have such function lambda, well, it's coherent to this point, yes. We have such function lambda, and any ideal intersect socle of A. So if kernel of lambda intersects trivially with socle, then it contains no zero ideals.
Usually a question arises, Julia was asked recently, that Gorenstein needs some symmetry.
Yes.
That you will discuss this?
For greater case, yes. But firstly, I will recall some facts on projective models and injective models. So, a model T is called projective if for any surjective homomorphism of models and some homomorphism f from P to n. There is homomorphism G from P to m such that f equals to composition of phi and G. So we have model P, we have some surjective homomorphism from m to n. We have here phi, here we have f, and for any such construction we have a homomorphism from P to m, which makes this diagram commutative. Obvious example of projective model is R3 models. Because if we have here a basis, then we just see the images of this basis. We choose some pre-images, and we just send this basis to this chosen images, and we obtain this commutative diagram. And in fact, in our case, all projective models are free models. Not in general, but for our A, local finite-dimensional. Actually, it holds for any local variable. Well, it's also easy to see because we can consider a submodel NP. And the portion P mod NP is a vector space. Over A mod M, which is equal to K. So if we can choose some basis here, so let's choose some elements, A1, Ak, in P, such that their images are basis of this vector space. Then we can cover our model P by free model. It follows from the Nakayama lemma that actually in this case P1, Pk generate P. Well, it's not obvious, but it's not difficult to check. So we can consider a map from AR, from free model AR to P, which sends A1, AR, A8 to A1, A1 plus AR. It's a surjective map. And we can use that our model is projective. So we can consider an identity map here.
AG.
Sorry?
And then AG.
Yes, thank you. So we have a homomorphism from P to K to AK, and it's injective because this is injective. And it's not difficult to see that in this case, AK is isomorphic to P, the image of G, plus the kernel of this projection. And if we take a quotient by MAK, then it will be isomorphic to PMP plus, let's denote it by K, KMK. And here we have vector spaces. This is k-dimensional vector space. And this is k-dimensional vector space. So this must be 0, but then k equals to nk, and again by Nakayamas lemma, we obtain that k is 0. So actually, P is isomorphic to the K. And there is a dual definition of injective model.
Second, what is the conclusion of this part?
So we prove that any projective model is free over local finite-dimensional algebras.
Over any local finite dimensional.
Yes. So if you consider, model Q is called injective. If for any injective homomorphism by and some homomorphism F from N to Q, there is a homomorphism J from N to Q such that F is the composition of J and F. So we have injective homomorphism. We have Q, and for any F from N to K, there is G such that F is composition of P and G.
And may I ask? So you prove that any projective model is free. It has nothing to do with Gorenstein. This is
Yes. It's true.
So what is the A?
Now I will give another characterization. So basically the sixth point will be that A is injective. But I will need to
As a model of itself?
as a model of itself, yes. Well, yes. So the definition of injective model is dual to a definition of projective model. So if P is projective, then if we apply or injective, then if we apply matrix duality, then D of P is injective or projective. Because matrix duality exact function, so projective models will go to injective models, and injective models will go to projective models. And since for Gorenstein algebras A is isomorphic to omega A is projective, then omega A is injective, so A is a projective, injective. So if A is isomorphic to omega A, which is D of A, then A is projective. This is injective, so A is injective. But the converse is also true. So if A is injective, Then d of A is projective, and finally generated. Then d of A is a free model. But if we compare dimensions, we obtain that actually are equal to 1. So d of A has and it's interesting because what means that some model is injective? In particular, what means that if A is injective? So in general, if we have some short exact sequence of models, then we can consider dual models. I recall that this is a homomorphism from M to A. And in general, we obtain this exact sequence, but this map will not necessarily be surjective. And actually, A injective means that actually this map is surjective. And actually, it's equivalent to be injective. So if A is injective, this functor is also exact functor. So this is a 7 definition.
But it may be not exact only in the case of infinitely dimensional models. Right?
Yes, exactly, on finitely generated models.
And finite generated means finite dimension.
Yes, here it's the same concept. Yes, I have 10 minutes.
But still, I don't understand. So, if you consider only finite dimensional models, but you can regard them as just vector spaces.
But these are not dual vector spaces.
It's not a dual vector space because we take over A.
Over A, okay.
So, yes, I will go faster now. So, consider a graded case now. We can consider a graded algebra. We assume that zero component contains only constants, and AK is not zero. Then it's obvious that the last component is contained in the so-called A. So if A is a Gorenstein, then AK is one-dimensional. And for any I, we have a linear map from AI and AK minus I to AK such that, AB goes to just a product. And this is just a one-dimensional vector space, so it's just a field, so it's a linear map. And it's non-degenerate. because if for some element A we have 0 for any element from AK, then we know that if we consider an ideal generated by A, it intersects non-trivially with circle. So there is B. Yes, such that AB belongs to circle, which is AK in our case. And it's clear that we can take B from AK minus I, yes, because A belongs to AI. So we can take just a homogeneous component from AK minus I. And it's not 0. So its form non-degenerate. And for graded case, it's also characterization of Gorenstein local algebras. So to be Gorenstein equivalent, dimension of the last component is equal to 1, and for any I, the map non-generated.
This also implies symmetries in dimensions.
Yes, exactly, yes. We know that we have a non-generated form only if dimension in particular. So let's prove to the other direction. So if we know that the last component is one-dimensional and this maps non-degenerate, while our algebra is Gorenstein, let's take some element A and suppose it starts from some AI. So it's from AI, it's non-zero. Then there is a B such that AIB is non-zero. So A B will not be zero. If K is not equal to, if I is not equal to K. B from maximal ideal is from A minus I. So A is Gorenstein. And the last characterization it says how we can represent Gorenstein algebras. So let's consider the algebra of polynomials. And we have the algebra of differential operators with constant coefficients. It's just isomorphic to algebra of polynomials. Well, here just we have simple modifications. So, for example, t xy on t xj. It's just so it's just an algebra of polynomials, and we can apply a differential operator to a polynomial. So actually, t is S module. And we can take some polynomial, non-zero, and we can consider annihilator of this polynomial. So such differential operators such that f is equal to 0.
What is this? F power 17?
No, it's non-zero. Yes, and actually for any non-zero f, the quotient of S by annihilator f is Gorenstein. Okay, I agreed. Okay. It's not equivalent. So actually, so there is a f non-zero such that a is isomorphic to S modular and f.
So any Gorenstein algebra can be realized this way?
Yes, but here I have some doubts because, well, it's an exercise in Eisenbach, and it says not specific like this. So it says that these algebras of this form are always Gorenstein. But in other direction, it's written not exactly like this. It's not written there that any Gorenstein algebra is of this form. But in my opinion, it follows from what is written there.
I doubt it.
Well, we can discuss it, but I see. So, okay, I will write what's written there. So it's written there that if you can consider ideal in S. Sorry?
It's for greatest case.
No, it's for which is contained and ideal generated by 1 by n, and S mod G Gorenstein, then annihilator of this ideal is one generated. So what Eisenbach is written in this situation. Okay, so this is all. Thank you for your attention.
Questions, comments?
In my opinion, very interesting talk, as it should be. So this is indeed useful for us. On a natural question, if you have any local algebra, right? You have this filtration by powers of maximum Laplace, descending filtration. But maybe also, as Polina told us yesterday, you have construct associated graded algebra, and Gorenstein property, is it preserved or?
No, it's not preserved. Yes,
No, not preserved.
arbitrary Gorenstein algebra, we don't have the symmetry on dimension of these quotients.
And also I would like to say that in our paper with you about any local algebra, we just took from classical sources, classification of local algebra of small dimensions. So up to dimension 6, this is some tables. Say in dimension 6 there are 25 local algebras, but this is some list of complete algebra. And starting from dimension 7, there are infinitely many local algebras. And we marked which algebras from this list are Gorenstein. But I would like very much to have the list of Gorenstein algebras only. What are Gorenstein algebra in dimension 1, 2, 3, 4, 5, 6, 7, and so on. And up to which dimensions there are finitely many of them. And the one believe he entered to this classification somehow, he used it, but as far as I understand, no table yet, right? So we don't know up to which dimensions the number of Gorenstein algebra is finite. Up to 9? So including 9? Yes. So we can do tables for 8, for 9, this will be finitely many concrete Gorenstein algebras.
Yes, classified to logical by here. I don't know, I'm sure that is logical about this.
Maybe it's also really interesting to have some kind of this table. I don't know whether this is realistic to make such table.
More questions,